Hi, everyone. Thank you all for joining. I'm Karine. I lead the developer community at StarTree. And I'm not going to take too much time to kind of jump right into it. But let's see. Sorry, I feel like I should have recorded again. I'm not ready. Let's see, hold on. So yeah, if you have any questions, please ask in the chat. And if you are not watching this live, you're welcome to join the Apache Pinot Slack, where our presenter Dunith is also there, but you can ask any questions there and we'll be able to answer them also if there's any follow-up questions. So the topic for today is analyzing IoT data using Apache Kafka and Pinot. And I will quickly introduce our amazing speaker, Dunith. He is a developer advocate at StarTree, helping people learn and use Apache Pinot for their user-facing analytics. Dunith is interested in stream processing, data analytics, and event-driven architecture. So Dunith, I will let you take it away and we'll catch up afterwards for Q&A.
Right. Thank you, Karin, for that awesome introduction. So everyone, good morning, good afternoon, and good evening from wherever you are joining in, and welcome to the session. Let me share my screen. Let me know once you can
see. We can see it.
Awesome. All right. So like Karin said, today's session is, the key objective of the session is to understand IoT analytics in very high level, and we'll discuss what are the typical components of IoT analytics system, and we'll try to understand minimal viable setup of or we can say a reference architecture for a typical IoT analytics system for your organization. And then we'll see how Apache Kafka and Apache Pinot fits into IoT system. Then also I put together a small demo towards the end of the session. So we'll see how Kafka and Pinot works together to build a small hypothetical fleet analysis system. Then in the meantime, I can take any questions, and feel free to post your questions in chat or ask directly. All right, so let's kick off the session. So first, what is Internet of Things? I know this has been a trending topic back, and it dates back to, goes back to 2010 and the beginning of the big data world. So actually, the big data and IoT is like hand and glove, so they share a lot of similarities. So by the official definition of IoT, it goes like a system of interrelated computing devices, mechanical and digital machines. I know it's a bit hard to digest, but at least it says interrelated something, right? So basically, you can simplify it as interrelated some devices with some computing power. So, for example, you can consider sensors of various appliances like GPS sensors, temperature sensors, smart meters of energy appliances, and there are so many things like wearable devices, agricultural equipment, and the list goes on, right? So they all have two things in common. First, they all connect to a network. So this network can be a private network, or it can be over the internet. So it doesn't matter. So what really matters is the interconnectedness of these devices. Secondly, they all bear a unique address. So that makes them individually addressable. So that's the gist of this IoT definition. And then they all produce data. So this data can be in structural data, and they can be also unstructured data. For example, so these sensors like temperature sensors can periodically produce their measurement temperature readings. So that can be in different formats like can be in binary, JSON, Avro, and there are many lists. And then there can be telemetry information, like periodic telemetry information, emitting in real time. Say, for example, if we consider a drone up in the sky, when it is operational, it can send its internal state as an event or a record. So the ground controllers can intercept it and act upon them accordingly. Also, this data can be in unstructured format like images and video. Say for that drone, it can send still images and surveillance footages as unstructured data. Also, there's a special thing about these data points. So each and every data point is tagged with a time series timestamp. So these are like time series data. So each data point carries when it is happened. So if you venture into stream processing further, you can find event time and processing time. So this basically represents event time. And then let's look at what do you mean by IoT data analysis. You know, this data, they don't sit there and rest, right? So we need to do some processing on that so we can derive some meaningful information. So this IoT processing or IoT analytics means the process of collecting and processing IoT data to derive actionable insights, right? So there are three things in there. So first thing is the collection, or we call it ingestion. So it's about collecting metrics, these data records or events from these IoT devices, and then storing it in a durable fashion, and then processing to derive some meaningful information, and finally acting upon this real-time information. So this could be like real-time triggering an alert and doing some sort of action based on that alert. Also, we can make real-time business decision to act on this data. So, like I said, big data, IoT is a subset of this big data domain. So the characteristics of big data analytics still also applies for IoT analytics as well. So in that case, we have this classic 3 V's of big data. It's the volume, velocity, and veracity. So IoT data, in a sense, so they arrive in high volume. So, you know, if you take any sensor or like a typical device, it could emit data in multiple volumes. Like if you collect multiple devices together, the volume is really large. And then the velocity. These devices are meant to emit events in very short periods. So the arrival rate is really high. So that's one challenge. Also, they have different shapes and forms, thus making them a wide veracity. So it can be structured data like strings or JSON formatted information, or could be like unstructured data like blobs and, you know, images and videos as well. So collecting this data in scalable fashion is challenging. Also, storing them in storage, scalable and economical fashion is another challenge. Also, processing them to meet strict SLA deadlines is another challenge. So that's why IoT analytics is something somewhat difficult to achieve even today if you can't find the right tool set. So in this session, we'll look at two famous tools we can use to build a typical IoT analytics system. All right, so in this section, we'll look into three characteristics or three fundamental types of analysis we can expect from a typical analytics setup. So it must be capable of delivering three types of analysis. First, the system should tell us what's happening right now. So this is about real-time analytics. For example, if an engineer in a manufacturing plant flow monitoring a dashboard to see what are the machines that are reaching high temperatures, right? So if a given machine reaches a high temperature threshold, an alarm must be triggered. So the operational engineer can take precautionary action, like shutting down the machine or increasing the coolant level. So that kind of thing. So that is about what is happening right now. And mostly these types of analytics is used by operational engineers and operational people. And then we have historical or descriptive analytics, and that actually tells you about why did it happen. So it's about the past. So if I continue the same example, so at a later point, we can dig into this time series data, right? So let's say the sensor has been emitting a set of data points. So we can always go back in time and slice and dice this data to figure out why did that alarm went off. So that kind of things you can do with this historical analysis. Usually this is performed by data analysts and BI engineers. So their main output is a dashboard or a report so that others can, like business leaders can take necessary action. Third type of analysis is predictive analytics. So that means what will happen next, what's going to happen next. So this is in the context of, we can apply this to, so we have historical data collected over some period of time, and then we can use this data to build a machine learning model. And we can use this data again to train this model so that.
Hold on, sorry, I'll mute that. Somebody's unmuted.
All right, no problem. All right, so I was on predictive analytics. So we can use this historically collected data points to build and train a machine learning model so that it can predict the outcome of the next thing. So probably, so we can consider predictive maintenance with respect to this IoT. So for example, if we are collecting a device metrics over a period of time, and we can apply smart machine learning models to provide or predict which machine has the most high probability of failing in the next hour, so that we can take precautionary measures. So those are the three types of analytics we can expect from any kind of IoT analytics setup. So based on those expectations, we can design a typical reference architecture for a typical analytics setup. So let me explain it from the left. So yeah, on the left-hand side, we have these IoT data sources. So this could be sensors, devices, or connecting through standard protocols. And then this data must be ingested in real time and in a scalable fashion. So data must be collected, transformed, and delivered to some sort of a temporary storage. So that's where streaming ETL pipeline can be plugged in. So we can consider variety of streaming ETL solutions here, like we can also consider Apache Flink or any other technology to build this kind of thing, pipelines. Also, if we can talk from Kafka's perspective, so this could be Kafka Connect. And when it comes to IoT data collection, Kafka also has this MQTT connector, so that you can deploy this MQTT connecting to Kafka Connect and have it collect and deliver MQTT formatted data into the event streaming platform. So this event streaming platform in the middle provides scalable and durable, also fault tolerant storage for incoming events. because, data arrives in high velocity and high volumes. So this data must be held or stored in somewhere before it is being analyzed by another system, downstream system. So that's the basis of this event streaming platform. So in today's technology landscape, we can consider multiple options for this. For example, Apache Kafka is the most prominent and popular choice in event streaming platforms. And then we have Apache Pulsar, AWS Kinesis, Azure Event Hubs, and there are so many options out there. And then we have an optional component, stream processor, because sometimes you need to do some real-time analytics or processing on the incoming data. So you don't have to wait and see, you don't have to wait and do some sort of action, but you need to respond to incoming events in real time. So you can do things like anomaly detection, rule execution, sort of things. So to do this kind of real-time processing, you can also consider Apache Flink, stream processors like Apache Flink, SAMSA, and then you can also consider Third Eye, which is like a sub-component in Apache Pinot architecture. So we'll be talking about this Third Eye in another meetup. And then we have real-time OLAP database. Actually, the purpose of this real-time OLAP database is to ingest data coming from this event streaming platform in a real-time and scalable fashion. So, and then this data can be accessed or queried in real time by various dashboard solutions, BI dashboards, custom applications like APIs, and then various exploratory data tools like Jupyter Notebooks and other Python or any other EDA solutions. And there's one component in this solution, so we can integrate this real-time OLAP database with deep storage, so that whenever data gets older, we can flush this older data into cloud-based storage location like S3 bucket or Google Cloud Storage, so that we can have an economical and scalable storage for your incoming data. So that's the typical reference architecture for a minimal viable IoT analytics setup. Now let's see what are the rest of the components. Yeah. So why Kafka? So this is a question you might have asked. So first reason, it's the scalable data ingestion we need to provide. Also, Kafka's design provides us fault-tolerant storage, and also with these consumer groups and other mechanisms, we can Kafka can support scalable data consumption. So there can be multiple consumers, downstream consumers for a topic in Kafka. So and then we can actually, let me go back. So this component, this architecture can be realized by having Apache Pinot as the real-time OLAP database, as well as Apache Kafka as the event streaming platform. And then why you might ask why are you using Pinot? Also in the last slide, is it just Kafka or can we use any other event streaming platform? And the answer is yes. So Pinot can integrate with mainly with Kafka, and then it can work with AWS Kinesis, and we have a connector for Pulsar as well. And then why Pinot? So if you go back to this diagram, you might see something similar to this Kappa architecture. So it is, in big data analytics space, we have two architectures, Lambda and Kappa. So Kappa architecture is like a unification of both, speed, real-time analytics, and batch analytics. So this is the holistic view of the Kappa architecture. So the best thing is Pinot can work as the serving layer for this Kappa architecture. So the main purpose is to answer ingest data in real time so that we can maintain the data freshness of for data, and then it can answer complex OLAP queries like time series queries on a high throughput manner. Then also Pinot can bring in additional indexing structures to enable high throughput queries like JSON indexes, and we also have support for geospatial queries, geospatial indexing as well. Also, like I discussed, Pinot supports integration with deep storage, so you can use Apache Pinot as a single place to keep your real-time new data as well as historical data in one place. All right, having said that, let's see this architecture in action. Okay, so just to realize this architecture, I put together with a small use case. So just imagine we are analyzing a fleet of trucks, right? Each truck is equipped with a GPS sensor. So in this demo, I'm using 4 trucks, and each truck has its sensor ID assigned to it. So for example, we have the sensor ID 100 representing a regular truck, and a speeding truck with sensor ID 101. So this speeding truck always exceeds its speed threshold. So we can witness that in a moment. Also, we have an idling truck. So it periodically moves and periodically it idles for some time. Maybe it's going through a traffic period. And then we have a truck going from San Francisco airport to the Golden Gate Bridge. So it's tagged with a geographical coordinate. All these sensor readings are going to a topic in Kafka. So this topic name is readings. And then we have configured a real-time table in Pinot called readings. And this table can ingest events coming from these readings in real time. Also, we have an offline table. I'll talk about that later. So this offline table serves as a dimension table. So it has the metadata about each truck and its metadata. So there's a one-to-one mapping between sensor and the truck that it connects. Also, then we have this consumption side. So these are the consumers of this analytics. So we'll be writing a couple of queries to analyze different use cases. So this data can be analyzed with the built-in Apache Pinot query console, and then we'll look at how this can be done with open source BI data visualization tool called Redash. And then finally, we'll connect a Jupyter notebook into Pinot through its Python driver so that we can perform exploratory data on the historical data. All right, without further ado, let me, right. Before jumping into that, let me quickly mention what are the features that we are going to discuss today. So first, we look at basic time series querying. Each event, each GPS recording is tagged with a time series, timestamp. So we'll do a series of time series filtering and group by and these kind of operations. And then we'll do a couple of geospatial query because each reading comes with a latitude and longitude pair. And then we'll do a lookup joins as well. All right, let me switch back to my terminal. All right, so my setup is running, my Pinot cluster is running in local machine. So if you go into So I have Docker desktop installed in my local setup, just to make it simple. So here I have this Pinot cluster up and running. So this, in Pinot, it's like a distributed system composed of multiple components. So first we have Zookeeper, also Kafka, and then we have Pinot controller, broker, and server. So if you are new to Pinot, so you can think of Zookeeper is the component that manages and coordinates all these communication and metadata management across all these Pinot components. And these are the basic Pinot components. So the controller is the main component that controls and the coordinates others. And then the broker, the Pinot server is responsible for storing ingested data in its configured data storage. And then broker is capable of receiving queries from outside consumers and scattering and gathering this query across multiple servers, and finally respond to the caller with the consolidated output. So in real life setup, practical deployment, you can see multiple instances of these Pinot servers, brokers, and controllers. But for the sake of this demonstration, I just run only one instance of this thing. And then I have Redash. This is my data visualization platform, and it is also running in a Docker stack. So I am not going to dig deeper into its internals, but you can think of it like a database, and it has this Progress internal database like this. And then I have this Jupyter notebook running as a separate container. Okay. So in Pinot, I have already created, I'm going into the query console here. You can type in localhost /9000. So I have already defined my two tables here. So if you go to query consoles, you can see readings and sensors here. So if I go back to my Visual Studio Code, you can see the schemas. So, schema is it's like a blueprint for this table. So this is the schema of the readings. So it has event ID. Each event has its event ID coming in, and this is a unique one. And the sensor ID. So sensor ID can be something in between 100 to 103. And the longitude and the latitude of the truck, right? And also we have some location data. So actually, by ingestion time, we convert the longitude and latitude, each longitude and latitude into ST point data type. So this is some native geospatial data type built into Apache Pinot. So then we use the ingestion transformation function here to transform it to this ST point data type. So this is going to be stored as a sequence of bytes. And then we have, so these are the dimension fields, and here we have the metrics fields. And this is where we do all the aggregations and other processing. So each reading contains the current speed, current fuel efficiency, like what's the how many gallons per mile, likewise, and then the timestamp. Right. So I have all the data in the readings table. Now what I'm going to do is I'm going to start one producer. So in the diagram I showed you, I have a regular producer called 100. So this producer, this is a Python client I just created to simulate the data publishing process. So when I publish this, it sends events into Kafka topic, the readings Kafka topic. And then what I'm going to do is I'll try to execute this query. Let me pull up my cheat sheet. Right, so what I'm trying to do here is this query returns the number of trucks or number of sensors who have published data in the last 5 seconds. So if you run this query, you will see one active truck because I have only one producer. And then I'll go ahead and start the second producer. So it has the sensor ID of 101. Now you can see the active trucks has been increased to 2. Actually, if I break down this query, so there's a time series filtering happens here. So this function is built into Pinot. So what it does is it converts this argument. So this is actually this should be in epoch milliseconds. So now returns the current time in epoch milliseconds. Also, since I want to get the last 5 seconds, so I'm subtracting 5,000 and then converting it to epoch seconds because timestamp is in epoch seconds. So that's how you get the active count. See, I think second publisher is finished. First publisher has finished. So that's why you see only one active truck in the moment. Second query is bit of interesting. This one, we are going to track who are the drivers or trucks who are actually speeding. So this query, so it's a typical SQL query. So we also do the filtering on this timestamp field. And then we group by all the sensors, readings by sensor ID. And we take the average speed and see whether for the last 5 seconds, if a given vehicle exceeds average speed of this limit or this threshold, we need to list them out. So that's what I'm going to do. I see 101 is still publishing it. Yeah, we can see one. Yes, because 101 is meant to be the high speeding driver. So if I start the 100 producer again, it's a good driver. So he drives below the limits, within the limits. Let's see whether, no, I think it's good. Okay. Yeah, so this is a typical time series analysis that you can do on this incoming data. So you might notice that the moment we publish data into Kafka, Pinot lets you analyze this data and get them queried. So that's the power of Pinot because the data, Pinot can ingest data in real time and guarantee that freshness of data is in seconds of time. It's not hours or days, it's seconds. So that is something crucial for your real-time analytics, especially when it comes to determine what's going on, right? Okay, and then we go to another type of analysis. This is called lookup joins. So if you look at this query result, you will see only sensor ID and the average speed. So basically, we need more information about the sensor. to be specific, we need to get the driver name who's driving this truck, also the name of the truck, which this sensor has been installed. To get this information, I'm using a lookup join. Basically, lookup join is like you join your real-time table with an offline table, which act as a small, slowly changing dimension table. So if you go into this sensors table, for example, I have defined it as an dimension lookup table. So if you have a primary key, and then you should be able to look up a particular record, then you can get the results from this table to enrich the final outcome. So for example, if you look at this table result, you'll see the driver name, truck name, and the corresponding sensor ID. I think so. We have like 5 trucks, 5 sensors, and 5 trucks in the system. So going forward, I'll run a query to enrich this result with this lookup table. Before that, let me quickly go through sensor schema, because there are a couple of things I need to show you. First thing, so this is the sensor schema. It only has this sensor ID, truck name, and driver name. But as a requirement, you must nominate a primary key column for sensor ID. Also, this table, sensors table, should be an offline table, and you should also nominate, or you should mark this table as a dim table true. Usually these tables must be smaller in size, and that's why you should allocate this kind of storage quota, like 200 megabytes and so on. You can find all this information in our StarTree blog. So there's a dedicated recipe for that. All right, now I'm going to execute this lookup join. Okay, there. So I don't have any records. So let me start this normal publisher again, and then run it again. All right. So basically, this query returns the sensor ID, you can see here, and performs a lookup with this sensors table and extract the truck name. So that's what you see here, and uses sensor ID as a lookup key. So truck name and the driver names also comes same. So yeah, that's about lookup joins. And then we have another thing called geospatial queries. Let me also quickly run that. All right. So in this query, if you remember, I talked about having a geospatial type in the schema of readings table. So that type actually stores the st point geospatial data type in the readings table. So currently what I'm doing is I'm trying to see the movements made by particular vehicle during last 5 seconds. If there are constant amount of movements, what we can assume is this vehicle, this truck is not moving. So it must be stuck in a traffic, or it must be idling. So that kind of analysis you can use to trigger an alert, idle alert, or some sort of thing. Right, let me first, let's run this and see whether any, okay. we don't have anything. Then I have this stationary publisher called 102. So what this publisher does is it always produces a fixed set of GPS coordinates. Let's see. Okay, only one movement. Right. So basically what it does is it use this geospatial function st point. So it can generate a st point by using this longitude and latitude of each event. And then it can count the number of occurrences in this using this distinct. If we have distinct 1, that means it hasn't been changed, or it hasn't been moved. So that's the basis of this operation. So that's about geospatial functions. And then we can continue to the second section of the presentation. That's about data visualization. So I'll make it quick since we are running out of time. So basically, when it comes to data visualization, Pinot integrates with many data visualization platforms, including Apache Superset, Tableau, and Redash. Actually, we are currently working in the Redash integration, and Redash will merge, we will do the direct integration in the late this summer. Also, considering for the future, we are currently working in progress for this Cube.js and Grafana integration as well. Since you've been, if you follow our YouTube channel, you can see many meetup videos based on Apache Superset. So that's why I thought of demonstrating Redash support in this meetup. So let me quickly switch back to Redash. So I have Redash locally installed in my machine, and it's currently running in local port 5000. So the basis of working with this, integrating this with Pinot is, first you have to go into settings, and you have to define a new data source. So for example, currently Redash doesn't have a direct integration with Apache Pinot, but it will come in the future. But for now, what you can do is you can create a new Python data source, and you can use this data source to run any arbitrary script, Python script. So that's the basis of our integration today. So, and this integration allows me to define multiple queries. Like, for example, if I go to average fuel efficiency query. So queries are like, these are like smallest elements in this Redash. So this allows you to run arbitrary number of Python scripts. So here what I do is I use this PinotDB driver, Python driver, to connect to Pinot from my Python script. And then I have specified the credentials of Pinot here. So it's using this PinotDB functions connect. And then also the queries pass through this like this. And then once we get the response, we need to convert it to a format supported by Redash. So that's what happens in this section. So this needs to be transformed. So once you do that, you'll be able to see something in the visualization, and then you can go there and pick your whatever the visualization type you want to do, because visualization is one critical thing when it comes to watching real-time data. So likewise, I have created different queries, like for example, what is the active fleet, and also who are the speeding trucks, and what is the average fuel efficiency of all-time trucks. So likewise, this dashboard consists of all these metrics. So Redash allows you to do automatic refreshing. So like 1 minute, 5 minutes, and so on. So let me publish a couple of readings here. So I'm starting all. Now, if you refresh this, you can see 3 active tracks because there are 3 active tracks publishing data into Pinot. And then you see 2 speed alerts. And also you can see the active fleets, and this includes information coming from the sensors DIM table as well. And this is coming from historical data table, historical information. This is like all-time average of fuel efficiencies of currently running trucks. We can see truck with 100, since ID 100 is having the highest fuel efficiency. Yeah, so that's about data visualization. And then also I have my final part. This is exploratory data analysis. I'll quickly run through this. So basically, like I said, Pinot provides you a Python library, PinotDB, to connect and query Pinot data from different Python applications. If you happen to watch Mark's previous meetup talk, he showed you how to use Streamlit to connect to Pinot and visualize that data. So basically, Streamlit also a Python library so that you can use it for exploratory data analysis. So in here, what I'm going to do is I'm trying to connect Jupyter notebooks to Pinot so that I can get access to Pinot data as pandas. You know, pandas is like data frames structures so that you can manipulate them using different ways so that you can plug them to different charting libraries so to get interactive data visualization. So yeah, I have this Jupyter notebook running as a Docker container. So simple, just one container. Also, I have this notebook created locally. So when I run this, so this is basically the average fuel efficiency coming from the readings table. So the code is similar to what I have written in the Redash. Only difference is the runtime is different. So I get the pandas data frame here, and then in that I'm passing it to my charting library called matplotlib. So likewise, you can slice and dice data stored in Pinot to meet your different expectation in real-time analysis. Right. So just to sum up what we have discussed so far. So we have seen Pinot is delivering both real-time and historical analysis on incoming data. So this real-time analytics capabilities can be used to build user-facing dashboards and operational monitoring things. Also, you can query streaming data on real-time queries on streaming data. And then Pinot allows you to do ad hoc queries on streaming data. So you can issue SQL complex OLAP queries on this historical data as well. And then you can plug different frameworks of data, exploratory data tools to query historical data so that you can come to different conclusions on how data has been changing over time. So that's how Pinot and Kafka are collectively addressing the needs of a typical IoT system architecture. So that's about our meetup. So I can, so since we have few minutes remaining, I think I can take a couple of questions.
Cool. Thank you, Dunith. That was awesome.
Thank you.
So does anybody have any questions? Like you could actually, because we don't have a big group, if you want to like, you can ask in the chat or you can actually turn your thing off of mute and you can ask questions directly. Eric gave a thumbs up. So I think that means good talk. This is really cool. Thanks for taking the time, Dunith.
No problem. My pleasure.
So Neha said, really good talk, Dunith, learned a lot, loved all the integrations. Eric, nice presentation, thanks. Cool, so if there isn't any questions, I think we could probably wrap it up. And if you do have any questions or you want to chat with Dunith and ask him questions, whatever, just conversate about stuff, you can join the Apache Pinot Slack and he's in there, you'll find him. Cool. Well, thank you everyone for joining and we'll see you at the next meetup.
Bye.
Bye.